NCBM 0324, Section 1.5, Basics of Factoring Polynomials, Part 2. In our last two examples, we were listing out the factors of 18 and 24. And then in example 3, they're asking us to list the common factors of 18 and 24 from examples 1 and 2. And then what is the greatest common factor? So let's start with the list here. So we want the common factors. Remember, each of these numbers is considered a factor since we're able to find a number to multiply by to get 18 or 24. So the common values, we're going to look to see what numbers both of these 18 and 24 lists, what numbers do they share. So we can easily see that they're going to share the number 1. They both have 1 as a factor. And we can easily see also 2. Right? They were both even numbers. So even numbers are multiples of 2, so that makes sense. And we can also see from our list, we have 3, and then we have 6. I don't have a 9 or an 18 in common, 12, nope. Those are my other common factors. So the common factors are going to be important for that idea of the larger factoring of polynomials. And to go with that, we look for the greatest of these common factors. So our greatest common factor, GCF, abbreviated, is that 6. 6 is the biggest out of all of these that we have listed. So 1 is going to be a common factor for all of our values, all of our expressions really, but it's not the greatest, and we want to look for the greatest of these common factors. So we're going to say then down here as a definition, the greatest common factor, or GCF, is the biggest or greatest factor that divides two numbers. So I could say up here that 6 is the biggest number that divides both 18 and 24. Maybe I'm going to add that as my little extra note to myself. 6, biggest number that divides into 18 and 24. There's nothing bigger that will divide nicely into those two numbers. So this GCF, it's going to be our first step in our larger factoring process because it's easy to recognize once we get the hang of it, and it's going to be easy to do the rest of the factoring once that GCF is taken into account. Now, another type of factoring that'll be important in determining this GCF is something called the prime factorization. And for numbers, we have a really nice method of finding that prime factorization. Let's try the number 18. So I'm going to start with 18, and I'm going to ask myself two numbers that multiply to give me 18. I'm going to find two factors to start with. And I don't want to do 1 and 18 because I already have the 18 started. But I'm going to write these factors in this tree-like shape. So I could say 2 times 9. 2 times 9 gives me 18. And then from those factors that I've chosen, I'm going to try to break those down even further. Well, 2 is simply 1 times 2. So in fact, 2 is considered prime because the only other factors are 1 and itself, and that's what it means to be prime. But 9 I can write that as 3 times 3. Right? 3 times 3 gives me that 9. And then I try it again. Can I go further down with 3? Well, the only multiples of 3 are 1 and itself. So again, we're at prime. And the same thing with the other 3 here. So then my prime factorization is going to be the factors from the lowest pieces of my branches. However, wherever we stop our branches, those lowest ones are going to be our prime factorization. So in this case, our 18, I can consider it 2 times 3 times 3. This will be the prime factorization of the number 18. And in case you're wondering, how do these differ from our answers from example 1? Well, if I look a little more closely at the numbers the factors that we got from example 1, they're all built from these three values. 2 times 3 gives me the 6, 3 times 3 gives me the 9, 2 is in there, 3 is in there. So any combination of these prime factors are going to give me the other factor answers we got in our example 1. And if I do the same thing for number 24, I can say 2 times 12. 12 is 2 times 6. And then 6 is 2 times 3. I can build a prime factorization for this one. 2 times 2 times 2 times 3 gives me that 24. Well, these are the values that I would need in order to make all these other factors we have listed in example 2. So that prime factorization will help us determine some of the factors, and it's going to help us find that GCF. In fact, let's try it. Let's do it from the trees. So in the tree case, right over here, what numbers do they have in common? Well, they both have a 2, at least one 2, right? They don't have two of them because the 18 only has one in its prime factorization. And then they have a 3 in common, but they don't have this other 3 because the 24 doesn't have another 3. So those are the values where they overlap. And what is 2 times 3? It's that 6, right? So it's all related to each other. And the prime factorization will be really nice. In some cases, others we may be able to list out the factors easily like we did in those other examples. It's all depending on the situation. But the more skills we have, the more we have to use when it comes time to apply some of this. All right, so let's put this together. Let's maybe formulate a little plan here. We're going to say to find the GCF of any type of expression or number, we're going to list the prime factors. So we're going to look at the prime factors of each of the values within our expression. And from that prime factorization, we're going to look for the greatest. What numbers do they have in common? That's going to give us the biggest factor overall. So let's try this in example 4. So this with numbers first. In example 4, we want to find the GCF of 14, 21, and 28. So I want the prime factors of each of these numbers to start. So I'm going to look at 14. I'll do a little tree here. Well, 14 is 2 times 7. And again, 2 is prime, 7 is prime. We can't factor it any further. So the prime factorization of 14 is simply 2 times 7. We'll do the same thing for 21. Let's see, 21 is 3 times 7. Again, 3 is prime, can't go further there. 7 is prime. So my prime factorization in this case is 3 times 7. What about 28? I know that's even, so I'm going to do 2. 2 times 14 gives me 28. And then I go a little further because I know 14 is also even, so another 2 times 7 gives me that 14 there. So in this case, my lowest branch values from each of the branches is 2 times 2 times 7. 2 times 2 times 7. So there's my prime factorization of 28. I can make all the factors of 28 from those 2, 2, and 7 numbers. Okay, so we're looking for now the greatest. What do they have in common? What do all of these prime factorizations each have? I think we can see really quick they each have a 7. So 7 is part of my greatest common factor. Do they each have a 2? Oh, the first one, the third one does, but the 21 did not have a 2, so that's not common. What about the 3? Oh, the other ones don't have 3s, so we've gone through all the possibilities. Our GCF in this case will be the 7. That's the greatest common factor that all of those numbers would have. They're all divisible by 7, and that's what the prime factorization helped us find. Let's try this now with some variables thrown in. Let's look at example 5. We want to find the GCF of 12x squared, 13xy, and 15xy squared. Okay, so prime factorization. We're going to start with those. Let's look at the numbers, the coefficients. I think I'm going to do a little scratch work here. I'm going to do my 12 down here. So 12 can be 2 times 6. And then 6 can be 2 times 3. Those are all prime now, so we're good. So in my first one, my 12x squared, I can write this as 2 times 2 times 3 times my x squared. Right? Think about that. It's just multiplied all the way through, and it means the same thing as 12x squared. Let's look at 13 now. 13, well, that's only 1 in 13, so 13 is already prime. We're good to go on 13. So we have 13 times x times y. We'll leave that as is. But what about the 15? Let's try the 15. I know it's 5, because it ends in 5, so there's a multiple of 5 here. And 5 times 3 gives me that 15. 5 is prime, 3 is prime, so we're good. So we'll say 15x times y squared is equal to 3 times 5 times x times y squared. Okay, so I have everything listed. All my primes are on here now. Then I look, what do they have in common? What numbers, and in this case also what variables, do they all share? Well, I don't think they have any numbers, right? I don't see any numbers that they all have, especially because we have this 13 in here, and none of the other prime factorizations have 13. So then my GCF, it's not going to have a number in it, but let's see about those variables. So in my first term here, I have an x squared. So that's like saying I have x times x. Then in my second term, I have x times y. So the first one didn't have a y, but they do both have an x. So I'm thinking maybe x is what they have in common. Just one of these, because the second term only has one x. But let's make sure our third one also has an x. Do we have an x over here? We do, right? We have this little x by itself here. Do they have anything else in common then? Do they have y's? I know these two terms have a y in it, but the first one doesn't, right? So these GCFs have to be in the factorization of all of our terms. So in this case, to summarize it all, what is our GCF for number 5? It's simply x. Because x is the only thing that they all three have in common. They don't have any other values, they don't have any other variables, any other powers. It's simply the x.